Hi students, I am V. Ragasuma. Welcome to my chemistry class. Today I am going to explain you about the crystal field theory. Crystal field theory is one of the complex compounds theory. In order to understand the bond between the metal and ligand, we have to understand about this crystal field theory. So previously I have explained you Werner theory, Sidgwick theory, and valence bond theory. This session, I'm going to explain you about the crystal field theory. In order to understand the crystal field theory, first we have to understand the shapes of the d orbitals. There are 5 d orbitals in the metal atoms. In the 5 d orbitals, 4 of the d orbitals are double shaped electron clouds, and there are 4 lobes. There are 4 lobes for the 4 d orbitals. And 1 d orbital, you are having 2 vertical lobes. And in the center, you are having saucer-like shape. The electron cloud resembles a saucer-like shape. So, these d orbitals are basically divided into 2 sets. One set is T2G set, the other set is EG set. So, dxy, dyz, dzx is T2G set. Dx square y square, dz square, dz square is EG set. Now, I'm going to show you the diagrams and explain the d orbital shapes, and now thereon we'll proceed for the postulates of the crystal field theory and the splitting of the crystal field theory. And this crystal field splitting in the octahedral complexes, tetrahedral complexes, and square complexes. So this session, I'm going to explain the postulates and the splitting of the d orbitals, crystal field splitting of the d orbitals in octahedral complexes. Now we'll see the d orbitals. Already I have told you there are 5 d orbitals. We have to, in order to understand the crystal field theory, first of all, we have to understand the shapes of the d orbitals, and we have to understand the orientation of the d orbitals. To understand crystal field theory, we should know the shapes and the spatial orientation in the transition metal. The first 5, so the 5 d orbitals are designated by dxy, dyz, dzx, dx square y square, and dz square. The first 4 orbitals, you can see here the 4 orbitals, not the center one. The 4 orbitals, you are having 4 lobes electron clouds, double shaped electron clouds. This blue part is the electron cloud. So there are 4, the 4 orbitals having electron clouds in between the axis. In between the axis. Once if you see, this is the axis, the Cartesians, the x, y, z. So in between you are having. So if it is x, y, if it is x, d, x, y, then the electron cloud. So these 4 orbitals having 4 lobes, double shaped electron clouds. This 1 orbital, 2 vertical lobes, the electron clouds, 2 vertical lobes along the z-axis. So we'll see why you are calling dxy. So dxy, between the x and y axis, you are having the electron cloud. And this is also between x and y. And this one also between x and y, x and y. Okay. This whole is the x-axis. And this complete one is the, sorry, This complete one is the x-axis and this complete one is the y-axis. Between x and y are there, and between x and 1 you're having the loop. Between the x and y you're having the loop. Between the y and x you're having the electron. So you call it as dxy between the axis. Now coming to the second one, you're having your y-axis, x-axis, z-axis. Now yz orbital between the z and y orbital. Here, in this orbital, the z-axis and y-axis. You're having the lobes between y-axis and the z-axis. Here, y and z. Between these two, you're having z. And again, here you can see this is the y and this is z. Between these two, you're having lobe. And here, this is the z and this is y. Z, y. Between these two, you're having the lobe. So the four lobes are between the YZ axis. Here the four lobes are between X and Z. This is X and this is Z. So okay. So once if you assume this is the Z axis and this is X axis, between these two Z and X you are having the lobes. And here it is along the axis. These three are between the axis. In between the axis, this is T2G set. And now this is x square y square. Along the x-axis you're having, along the y-axis you're having. So this is x square y square. Z is completely. And now coming to, so these four you're having double shape and four electron clubs, four lobes, electron clubs. Okay. So these four are one type and this is a different one, dz square. So this is square. So this is the z-axis, z, y and x. Here there is no concentration of any electron club. It is completely on the z-axis. On the z-axis you are having two vertical lines and saucer-like shape. This is dz square. So this is along the z-axis. These two orbitals are along the axis. So you call it as EGZ. These three are in between the axis. So this is T2G set. So I hope you have understood the orbitals, d orbitals in the central metal atom of a complex. Now we'll go for the postulates of the crystal field theory. Okay, so the 5 d orbitals we have seen, and now double shift. Now orbitals, whatever they are having, generally d orbitals they are having here. Beeth and Van Vleck has proposed this theory in 1930. This is completely electrostatic theory. You can call it as the electrostatic theory. This theory, crystal field theory, can otherwise be called as electrostatic theory. Beeth and Van Vleck proposed this theory. So the interaction between the metal ion and ligand is purely electrostatic. It means that the metal acts as a cation and the ligand acts as the anion or a neutral species. So completely by electrostatic attraction, the interaction between these two is just like the ions. So the plus ion, cation and the anion. So there will be electrostatic attraction. So 100% ionic. So the interaction between metal and ligand is 100% ionic and it are having the electrostatic attractions. The ligands are treated according to Beeth. The ligands are treated as just the point charges. They're treated as the point charges. Now, depending upon the ligand electrostatics, here the electrostatic attractions are of two types depending upon the ligand. Depending upon the ligand electrostatic attractions, the ions. There are two types electrostatic attractions. Depending upon the ligands electrostatic attractions, two types. One is ion-ion. That means if the metal is cation and the ligand is anion, then that is ion-ion attraction. So between the metal and the active ligand. If the metal is cation, the complex compound central metal, it is cation, and the ligand is neutral with no charge, then that you call it as dipole. So that type of attraction, that type of electrostatic attraction are ion dipole attraction. They are called as the ion dipole attractions. Okay, so electrostatic attractions are of two types, ion-ion and ion dipole. Now, the next postulate is the negative charged electron cloud of the ligand repels valence electron. You go for, just assume the metal, it is having d electrons, outermost shell d electrons are there. So the electrons are negative charged. Similarly, another ligand is coming in order to give its two electrons to the empty orbitals. While it wants to give its it wants to give its pair of electrons to the central metal with empty d orbitals. The innermost electrons are negatively charged. Innermost electrons are present, they are negative charged electrons. So the negative charged electron cloud of the ligand repel valence electrons of the metals. Now I've told you, empty orbitals will be participating. Along with that, you'll be having some innermost electrons also, now in the valence shell. So those valence electrons and the negatively charged electrons, they both have some repulsions. So ligand, incoming ligand is having electrons, that is negative charge. And again in the valence orbital, you are having empty orbitals as well as some of the valence electrons. Even these are having empty charge. These both have some repulsions. But still, the ligands are forced, but still they're forced to occupy the d orbitals of the metal. Okay, so the ligands come, occupy the empty d orbital where the valence electrons are there. According, they're forced to occupy the d orbital, which is not in the direction of the attacking. Okay, so the metal atom is having some valence electrons and empty orbitals. Now the incoming ligand will be having negative charged electrons, and that is approaching the metal atom. So the ligand approaches and it is forced to occupy metal in such a way that the attacking ligand is not in the direction of the valence electrons. Now the d orbitals degeneracy is lost. I have to tell you a word, degeneracy. What is degeneracy? Degeneracy means once if you see d orbital, almost all the d orbitals in absence of ligands, they have same energy. So the energy of the d orbitals is same. So they are called as degenerate orbitals. Orbitals with same energy are called degenerate orbitals. Generally, all d orbitals are degenerate orbitals. Okay. So in absence of the ligands, once if the ligand approaches, the degeneracy is lost. Energy difference comes between the d orbitals. We have seen 5 orbitals, they are having same energy, they are degenerate. But once if a ligand approaches the metal atom, in the metal atom, the d orbitals, in the d orbitals, you're having 5 d orbitals. They change the energy. They have, some of them, they gain the energy, some of them, they lose the energy. So degeneracy is lost. A difference in energy arises. So degeneracy is lost. Okay. So here, the negative electron cloud approaches the valence electrons and it is forced to occupy which are not in the direction of the ligand. So the metal atom is having some of the electrons. So the electrons against to the electrons, valence electrons direction, the attacking of the ligand takes place. Now, relative energies of the d orbitals will be different for different ligands. So if it is stronger ligand, one sort of energy the d orbitals will show. If it is a weaker ligand, it gives the other type of energy. So the relative energies will be different for different ligands. Crystal field is determined by number and arrangement of the ligands. Crystal field determined. So the splitting is determined by the number of the ligand and arrangement of the ligands around the centromere. So the d orbitals degeneracy lost and the splitting takes place. That is determined. It is governed by number of ligands and the position of the ligand. around the central metal atom. Now, the magnetic character depends. The magnetic character depends upon the depending upon the splitting of the d orbitals. Splitting of the d orbitals. So, our degeneracy of lost and attains different energy. Degeneracy is lost; they attain different energies. Relative energies of the d orbitals will be different for different ligands. The crystal field it is determined by the number and the arrangement of the ligands around the central middle. The magnetic character depends upon the extent of the splitting. It depends upon the extent of splitting of d orbitals by the ligands. Okay, greater splitting, greater is the splitting, lesser is the magnetic character. Less will be the less will be the electrons. Greater is the splitting, lesser will be the magnetic because unpaired electrons will decrease. If more splitting, unpaired electrons decrease. Therefore, magnetic character also decreases. Now, if it is lesser splitting, there will be more number of unpaired electrons, and therefore, we'll be getting more magnetic nature. Okay. So the color of the complex is explained on the basis of electronic transitions. Color of the complexes is explained on the basis of the electronic transitions between the d orbitals of different energies. D orbitals of different energies will have some different dd transitions, and thereby the color of the complexes is observed. I think you got this point. Once again, I'm repeating. Color spectra of the complex explained on the basis of electronic transitions, that is dd transitions. So different energies will be having different dd transitions and different electronic transitions, and thereby the color will be changed. Different colors will be coming for the different materials. Now, 3d orbitals, as I have told you previously, 3d orbitals have orientation between the coordinate axis. I have shown you dxy, dyz, dzx. They are between their axis. So dxy is between y and dxy is between the dx and between the dy axis. So the lobes are between the x-axis and the y-axis. So you call it as dx. For dyz, the lobes are in between the electron clouds. The lobes are between the y and z axis of the d. And coming to the dzx, the vertical lobes, 4 lobes are between the x-axis and z-axis. So you call it as dzx. Now coming to the 2d orbitals have orient in x3 orbitals, they are called as the t2g set, between the ones which are between the coordinate axis. The 2d orbitals have the orientation along the axis. So they are called as the EG set, dx square, y square. Now the conversion of the 5 degenerate d orbitals of metal ions into the 2 sets into 2 different is nothing but crystal field splitting. You are having 2 sets. One is the 3d orbitals T2g set, and the other one is the T2g EG set. So the conversion of 5 degenerate d orbitals of the metal ions, 5 degenerate orbitals into 2 sets of orbitals of different energies is called crystal field splitting. So now we'll see the splitting, how it takes place. Now we'll see here, I have told you, this is the energy of the orbitals, degenerate d orbitals, dxy, dyz, dzx, dx square, y square. All the 3 are on the same line. What it means? On the same energy. These are called degenerate orbitals. Now this is the metal atom. So this is metal atom. Valence d orbitals of the central metal atom. They are degenerate. 5 orbitals having same energies. Now, as the ligand is approaching, as the ligands are approaching, the energy is rising for these 5 orbitals. Degeneracy. degenerate d orbitals in presence of ligands. What you are able to say? Energy is increasing. Previously, it is only this much. Now, it has increased in presence of ligands. The energy has increased. So, this is the way. Okay. So, this session, what I've told you is, I have explained you now the postulates. I have explained you about the shapes of the d orbitals and the crystal field postulates. What is degenerate? What is how they are getting split with C for octahedral complexes. Now, in the octahedral complex, we'll see the splitting, crystal field splitting. Octahedral complex, just I remember one, ML6. So octahedral complex means ML6, metal atom, M, L, ligands. They are in 6 number. Coordination number is 6. They are called as the octahedral complexes. The 6 ligands approach metal ion. You can assume 6 ligands are approaching metal ion along the axis. Along the axis. See, here is the central metal atom. You are having the ligands 1, 2, 3, 4, 5 and 6. Okay, 6 ligands. Here x coordinate axis, y coordinate axis, z coordinate axis. You are having 6 ligands 1, 2, 3, 4, 6. Okay, so 4 around, up to 1, down 5 and 6. 6 ligands. Okay, in the central metal atom you are having d orbitals. The central metal atom you are having d orbitals, degenerate. So T2G set is in between the coordinates. Here metal d orbitals, 3 d orbitals are between the coordinate axis and 2 orbitals are along the coordinate axis. T2G set and EG set are present in this metal. Now ligands are approaching in the direction to occupy metal orbital where there are no valence electrons. They are forced to occupy. The ligands approach the central metal atom and they are forced to occupy d orbitals where there are no valence electrons. Okay, in order to avoid the repulsions. So now we have seen central metal atom, 6 ligands, and this metal atom is having d orbitals, 2 sets, T2G, EG set. Now how the splitting is going on, we'll see. Before this bonding takes place, there is crystal field splitting in the metal, d orbital. Before, here there is a metal, ligands are approaching. Before the ligands approach, bond with the metal, there is crystal field splitting, splitting of d orbital, losing of degeneracy of the d will take place, and thereby they bond with the ligand. After splitting, then bonding of the ligands will take place. Now we'll see the splitting. We'll see. You can see here. Okay, this is the way they are arranged. So ligands in the just to see here very clearly, the ligands are in the direction of axis. Okay, they are in the direction of axis. This ligand along x, this ligand along y, this ligand along x, this ligand along x, this ligand is along y, this ligand is along z. I hope you have understood clearly. Okay, so central metal atom, d orbitals are present. Now the ligands are approaching. In which way they are approaching? They are approaching along the axis. This is the main point you have to understand. They are approaching along the axis, along the 2 ligands. Here, 2 ligands along x-axis, 2 ligands along y-axis, 2 ligands along the z-axis. Now, what will happen is, while they're approaching along the axis, here, energy of the EG orbitals, 6 ligands approaching metal ion along the axis. Energy. Now, EG set. What is EG set? Energy of two EG orbitals. Energy of two EG orbitals, that is dx square y square dz square, which are oriented along the axis, increases because in their direction ligand is coming. Ligand is coming in their direction. Dx square y square dz square are along the axis. You are having 5 orbitals and this EG orbital, they're along the axis. Now ligands are also coming along the axis. So these will experience greater repulsions with the ligand. Okay, due to the greater repulsions between the ligand and EG orbitals. So energy is increased. Energy of EG orbitals, that is dx square dz square, these are oriented along the x-axis. Therefore, as the ligand is approaching, greater repulsions will take place for the ligands along the axis, that is EGC, and thereby energy is increased. Okay, I hope you have understood. So central metal atom is there, ligands are approaching along the axis. So along the axis, you are having only 2 orbitals, 2 EG orbitals, dx square y square dz square. So these orbitals experience more repulsion because ligand is minus and the d orbital electrons also minus. They experience more repulsions and energy is increased. Okay, now next one, energy of T2G orbitals. T2G orbitals means what you remember, dxy, dyz, dz. These are oriented between the axis. These are oriented between the axis. Okay, so now, so between the axis they experience less repulsion. Okay, so where the repulsion is more, the orbitals which are along the axis experience more repulsion. The orbitals which are in between the axis experience less repulsion. Therefore, energy of the T2G orbitals oriented in between the axis decreases. Energy will decrease. Okay, so metal ion, ligands approaching along the axis. So 5 orbitals, 2 will experience, 2 EG will experience more repulsion as they're along the axis. And 3 orbitals which are between the axis experience less repulsion. Therefore, energy of more repulsed orbitals will increase. Energy of the less repulsed will decrease. So these orbitals experience less repulsion and therefore energy will decrease. Okay. So now next, what will happen? The energy difference has come for the d orbitals. Actually, they are degenerate orbitals. As the ligands are approaching, one is experiencing more repulsion and more energy. The other set is experiencing less repulsion and less energy. Therefore, energy difference has come between them. So there is a splitting of the orbital, EG and T2 orbital. They have experienced the energy difference. Therefore, they have splitted into 2 sets. One is T2G set, the other one is EG set. That splitting is called as crystal field splitting energy, denoted by delta O. Octahedral complexes, delta O. For tetrahedral, delta T. Delta is Q for square. So delta O, energy difference between the EG and T2G. This is called as the crystal field splitting energy. The conversion of, I'm repeating, the conversion of 5 degenerate d orbitals of metal ion into 2 sets having different energies is called as crystal field splitting. This is called as the crystal field splitting. Okay, so this is what I have explained. I hope everybody have understood. So Previous sessions, complexes, bonds, Werner theory, Sedgwick theory, BBT, everything on. Now we have seen the crystal field splitting. Before understanding the crystal field splitting, we have seen the orbitals. We have seen the orbitals, how they are arranged, how is their alignment, and then what are the postulates of the crystal field theory we have seen. He has explained that attraction is 100% ionic and the ligands as the positive charges, and the interactions are of two types, ion-ion and ion dipole attractions. The negative charge electron cloud of the ligand is forced to occupy which are not in the direction of the metal valence electrons. The degeneracy is lost. Okay, so and thereby splitting takes place. Relative energies are different for different ligands, and crystal field is determined by number and arrangement of the ligands. As the ligands are more and the arrangement is depending upon the arrangement of the ligands around centimeter, the crystal field will experience splitting. Magnetic character, it depends upon the splitting of the d orbitals. More splitting, less magnetic. Less splitting, more magnetic character. Okay, so the I've told you previously, greater splitting, less magnetic character means you are having the paired up electrons. Greater splitting. So you'll be having greater splitting is there, less magnetic character. You'll be having all paired up electrons. Less magnetic character means paired up electrons. So lesser splitting. If you will see the lesser splitting, you can see more magnetic. You can see more number of unpaired electrons. Therefore, more magnetic character. And the color by the DD transitions, the color and spectroscopy explain depending upon the electronic transitions. You can explain the electronic transitions. Okay, and d orbitals I have explained two sets, T2G set and EG set. All the set are previously degenerate, and after splitting, then after getting a difference in energy, they get splitted and the degeneracy is lost. Okay, so the degeneracy is lost. Now we'll see the diagram, how it's getting split. The most important one is the diagram. Now coming to this diagram, we'll see metal ion. I have explained you. This is the central metal ion. Central metal ion, the ligands. Okay. So ligands are along the axis, 6 ligands. So thereby splitting takes place accordingly. Here, this is the energy. In the metal d orbitals are 1, 2, 3, 4. So dxy, xz, dzx, and dyz, dz square, dx square. 5 orbitals. They have the same energy. These are called degenerate orbitals. Now ligand is approaching. Here you can see that ligands are approaching. What happens? Energy is increasing. Previous diagram. Energy is increasing. Here, all of them are degenerate orbitals in the metal. As the ligands are approaching, energy has increased. Average energy has increased. The crystal. Now the splitting has taken place. The ligands have approached more nearer. Now the ligands along the axis, that is EG set, that is x square, y square and dz square, EG set. They experience more repulsion, they gain more energy. Here. This is the actual energy. Here it has increased the energy. This is the energy of the d orbitals in presence of ligands. Now, still these are degenerate, but the energy is increased. Degenerate, all of them having same energy, degenerate orbitals, but their energy is increased than previous condition. So they're having the same energy, degenerate orbitals, but previously compared to the previous, the energy is increased. Now these, as the ligands approach nearer, these have split into two sets, EG set and T2G set. EG set and T2G set. EG set is the orbitals dx square y square dz square. These are along the axis experiencing more repulsion, gained more energy. So compared to this energy, the energy is more. Compared to this energy, T2G set between the lobes, so less repulsion, less energy. Energy has decreased for T2G set. EG set it has increased the energy. So therefore, due to this energy difference, they have experienced the splitting. Okay, so 10 dq, it is 10 dq. Now you can see delta O, the difference in energy is 0.6. It is 0.6 delta O, and here it is 0.4 delta energy. Okay, now these are split into two types. State 1, here you can see the state 1, degenerate orbitals. Here, this one I'm explaining. This is state 1, state 2, state 3. I'm explaining state 1, state 2, and this is state 3. What is happening? State 1, all of them are degenerate orbitals of free metal. State 2, degenerate orbitals of the metal ion, higher energy, with higher energy. State 3 is splitting of d orbitals in the octahedral field. So every electron, each electron that enters in the T2G orbital, stabilizes the complex ion by 0.4 delta O. Whatever electron that is entering T2G set, stabilizes the complex. So whatever electron is entering into this T2G set, this is one orbital, this is one orbital, this one. Whatever electron that enters T2G set stabilizes the whole complex by 0.4 delta by 2 by 5 delta 0.4 delta. 2 by 5 delta is nothing but 0.4 delta. Next, each electron entering into the EG set destabilizes the complex ion by 0.6 delta. 3 by 5 means 0.6, 0.6 delta. That is the difference in energy, delta. Okay, so this is the way how the splitting is taking place. In the octahedral complexes. So you have understood the shapes of the d orbitals, the postulates of the crystal field theory. Okay, and now the different orbitals, different types. Next, how the degeneracy is lost, and crystal field splitting of the octahedral complexes, how the ligands are approaching, as they are approaching, how the octahedral complexes, crystal field splitting taking place, how the crystal field splitting in the octahedrals is taking place. Central metal ion, as the ligand approach, energy increase. As the ligands approach to be bonded, immediately the energy differences come and splitting is take place. This is called crystal field splitting. This is the difference in energy. Okay. Here, as the electron enters, it destabilizes the complex. As it enters T2G set, it stabilizes the complex. Okay, state 1, state 2, and state 3. We have seen. I hope everybody have understood this session. Thank you. And next class, I'm going to tell you the crystal field splitting in tetrahedral complex and the crystal field splitting in the square planar complexes. What is a low spin, high spin complex? All this will be explained next session. Thank you, everybody. Thank you, everyone.